Welcome to Introduction to Mathematics for Machine Learning. Machine learning is about designing algorithms that automatically extract valuable information from data. The emphasis here is on automatic. That is, machine learning is concerned about general-purpose methodologies that can be applied to many data sets while producing something that's meaningful. There are three concepts that are at the core of machine learning: data, a model, and learning. Since machine learning is inherently data-driven, data is at the core of machine learning. The goal of machine learning is to design general-purpose methodologies to extract valuable patterns from data, ideally without much domain-specific expertise. To achieve this goal, we design models that are typically related to the processes that generate data, similar to the data sets that we're given. To paraphrase Mitchell, a model is said to learn from data if its performance on a given task improves after the data is taken into account. The goal is to find good models that generalize well to yet unseen data, which we may care about in the future. Learning can be understood as a way to automatically find patterns and structures in data by optimizing the performance of the model. We think of data as vectors. We assume that data has already been appropriately converted into numerical representation suitable for reading into a computer program. We note that there are at least three different ways to think about vectors. We can think about a vector as an array of numbers, like we would if we're taking a computer science class. A vector could also be thought of as an arrow with direction and magnitude. That's the physics point of view. A vector can also be thought of as an object that obeys addition and scaling. That's the mathematical view. A model is typically used to describe a process for generating data similar to some given data set. Therefore, good models can also be thought of as simplified versions of the real unknown data generating process, capturing aspects that are relevant for modeling data and abstracting hidden patterns from it. A good model can then be used to predict what would happen in the real world without performing real-world experiments. Let's assume that we have a data set and a suitable model. Training the model means to use the data available to optimize some parameters of the model with respect to a utility function that evaluates how well the model predicts the training data. We summarize the main concepts of machine learning that we covered in this video series. We represent data as vectors. We choose an appropriate model, either using the probabilistic or optimization points of view. We learn from the available data by using numerical optimization methods with the aim that the model performs better on data that was not used for training. Four pillars of machine learning require a solid mathematical foundation. We represent numerical data as vectors and represent a table of such data as a matrix. The study of vectors and matrices is called linear algebra. Given two vectors representing two objects in the real world, we want to make statements about their similarity. The idea is that vectors that are similar should be predicted to have similar outputs by our machine learning algorithms. To formalize the idea of similarity between vectors, we need to introduce operations that take two vectors as inputs and return a numerical value representing their similarity. The construction of similarity and distances is central to analytic geometry. We will also need some fundamental concept about matrices and matrix decomposition. We often consider data to be noisy observations of some true underlying signal. We hope that by applying machine learning, we can identify the signal from the noise. This requires us to have a language for quantifying what noise means. We often would also like to have predictors that allow us to express some sort of uncertainty. All of this is part of probability theory. To train machine learning models, we typically find parameters that maximize some performance measure. Many optimization techniques require the concept of a gradient, which tells us the direction in which to search for a solution. So we need vector calculus and continuous optimization. Clearly, we need a wide array of tools to approach machine learning properly. Here are the 4 pillars of machine learning. Linear algebra. The goal is to find functions that map d-dimensional inputs to corresponding observed function values y, which we can interpret as the labels for the inputs. Dimension reduction. The goal here is to find a compact, lower dimensional representation of high dimensional data, which is often easier to analyze than that high dimensional data. Unlike regression, dimensionality reduction is only concerned about modeling the data. There are no labels associated with the data points. Density estimation. We want to find a probability distribution that describes a given data set. We'll focus on Gaussian mixture models for this purpose, and we will discuss an iterative scheme to find parameters of this model. As in dimensionality reduction, there are no labels associated with the data points. However, we do seek a low-dimensional representation of the data. Instead, we're interested in a density model that describes the data. In classification, we discuss classification context to support vector machines. Similar to regression, we have inputs X and output labels Y. However, unlike regression, where the labels are real value, the labels in classification are integers, which require some special care. Hopefully, you have a better understanding of the mathematics required for machine learning. In our upcoming videos, we will dive into these topics further. Goodbye.